Hey everybody, welcome to section 3.3.2, complex numbers. Last section, we added them, we multiplied them, and now we're going to raise them to exponents, and we're going to divide, and we're going to do some more solving. So, let's talk about exponents. Powers of I. Well, you already know that I to the first power, it's just I, and we know that to be square root of -1. And we already talked about how when you square both sides of I is equal to -1, you get this. And the radical cancels with the exponent. You just get -1. It's the contents of what was inside the radical. What about I to the 0? And it might actually be, you may or may not remember from Algebra 1, or your Algebra 1 teacher might not even have taught you. But there's a pattern. We'll see the pattern in a moment, and I'll work it backwards. Like you'll see that there's actually the pattern will hold, and you just run the pattern backwards and get to 1 here. But if you wanted to, even just forgetting imaginary numbers for a moment, you could take 3 squared and divide it by 3 squared. And what is that? Well, anything divided by itself is 1. But also, you remember that if you subtract exponent, the subtraction exponent rule says that you can take this 2 and this 2 and subtract them because the bases are the same. So that's 2 minus 2. 2 minus 2 is 0, so 3 to the 0 must equal this, which must equal 1. 3 to the 0 equals 1. You can even ask your calculator. Like, you can pause the video and ask your calculator, what is 3 to the 0? Any calculator will tell you it's actually equal to 1, which is a very strange idea. A lot of students expect it to be equal to 0, but it's not. 3 to the 0. 5 to the 0 equals 1. 10 to the 0 equals 1. 200 to the 0 equals 1. Even I to the 0 does equal 1. You could ask your calculator that too. Pull it out and say, what is I to the 0? It'll tell you 1. So that's why that is what it is. So what is I to the third power? Well, I to the third power would just be 2i. I times itself 3 times would be I squared times I to the first power. And we know what I squared is. That's -1. So when you simplify this, I to the third is just -I. What is I to the fourth? Well, I to the fourth is the same thing as if you're multiplying I by itself 4 times. It's I times itself twice times I times itself twice. And we know what I squared is. That's -1 times -1, which is +1. There's a theme here in math generally that anytime you come up with something you don't know, you turn it into something that you do know, and work backwards from there. So we didn't know what I to the fourth was, but we did know what I squared is. So if you can take this to something you don't know into something you do know, then that's helpful. And that's how you build new knowledge in math. Always. So I to the fifth. I don't know what I to the fifth is, but I do know what I to the fourth is. I to the fifth would be I to the fourth times I to the first. I to the fourth is just 1. So 1 times I is going to be I. I to the sixth, well, it's actually easiest to think of things as I to the fourth, because I to the fourth is a super easy number. It's just 1. I to the fourth turns into 1. I squared will turn into -1. Remember, that's what I squared is. It's one of the kind of key central facts that keeps on coming up over and over again. I squared is equal to -1. So if that's true, 1 times -1 is just going to give you -1. There it is. I to the seventh is just going to be the same thing as I to the fourth, because 4 plus 3 is 7, and so 4 of them turns into a 1, and I to the third, we found it over here. It's I to the third is -I, so 1 times -I is -I. I to the eighth. 8 is the same thing as 4 plus 4, and the I to the fourth is super easy to calculate. That's just 1, so 1 times 1 is still 1. I to the ninth. Well, we're starting to notice a pattern here. Every time you have an I to anything higher than I to the fourth, you just remove I to the 4 i's, and they're all going to equal 1. And so therefore, if I know that 9 divided by 4 is 2 remainder 1, that means I'm going to have, like here, 8 divided by 4 is 2. That means I'm going to have 2 sets of I to the fourth, one here and one here. If I'm going to write all the i's out here, all 9 of them, there would be 2 sets of 4 and then 1 left over. So I to the ninth is the same thing as I to the first. I got this 1 from the remainder because this is how many sets of 4 I'm going to have. They're all just going to be 1. It's going to be 1 times I to the first, which is just I. So, I to the 38th. I'm not going to write out 38 i's. There's a better way. There's an easier way. I can say 38 divided by 4 is 9 root 2. Because I divided by 4, I'm going to know that there are 9 groups of I to the 4th, which all just equal 1 when you multiply them. And there's going to be 2 left over. The remainder is 2. So really, you got to focus on the remainder, and you can say that I to the 38th is the same thing as I squared, which is -1. I keep on doing that. Let's see. I to the 401st power. I'm not going to write out 401 i's. It's ridiculous. What I can do is I can just take 401 divided by 4 and know that there are going to be 100 groups of I to the 4th and then 1 left over. All those groups are going to simplify to 1, and it's just I to the 401st is the same thing as I to the 1, which is I. So the big idea here is when you're simplifying I to the n, the answer will be either 1, I, -1, or -I, depending on the remainder after dividing the exponent by 4. And so you can pair these up. If the remainder is if the remainder is 0, then the answer is 1. If the remainder is 1, the answer is I. If the remainder is 2, the answer is -1. If the remainder is 3, the answer is -I. That still works for even here. For lower numbers, like 2 divided by 4 is 0, remainder 2, which is -1 here. Okay, so that's that. Remember to divide by 4 and focus on the remainders. If you had a complex equation, a complex equation is an equation that has complex numbers as either the coefficients or the answers. So here is x minus 16i. The variable here is x and the variable here is y. There's 2 variables. That's okay. You can actually split them up. If you're going to equate complex numbers, you have to solve for both x and y. This complex equation generates 2 different equations. It generates a real one and an imaginary one. And I've color-coded it so that you could see here are all the real parts, and here are, the real parts are red and the imaginary parts are blue. And you can split them up. 5x minus 7, those are the real parts, plus y plus 4i equals 13 plus 11i. Remember, this is because everything has got to be, all the real parts have got to equal each other and all the imaginary parts have got to equal each other. That's the equation you can actually set up. You got 5x minus 7 is the real part over here, equals 13. So equate the real parts and equate the imaginary parts and just solve like it's algebra 1. Notice when I write the imaginary parts, you don't need to write the I. You know that whatever y is going to be, when you add 4 to it, it's got to be the same as 11. So y plus 4 is equal to 11, or y equals 7. Let's take another example of that. Here, we've got the real parts in red and the imaginary parts in blue. So 5x plus 13 is equal to -2 because these are all the real parts. They've got to equal the real parts over here. And the blue part, it's got to equal the blue part. And that's what that is. Solve it like it's algebra 1. Here, x is the real part because there's no I. 3 is the real part, there's no I. But minus 16 and minus 2y those are the imaginary parts. You can write it with no imaginary numbers and solve it like it's algebra 1. So what you got to remember is the big idea is when solving an equation of complex numbers, you can split it up into both the real and imaginary equations. Dividing. Okay, so we've added complex numbers, we've subtracted, we've multiplied, and now we're going to divide. And the way we're going to do that is we're going to be rationalizing the denominators. So let's review a little bit. A couple of things to know is that when you divide by a fraction, it's the same thing as multiplying by the reciprocal. That's going to come in handy. And remember, if we're going to... So basically, the short version is that we're going to change division into multiplication by taking the reciprocal. And if we ever need to multiply complex numbers, because you can see we're changing division into multiplication. And how do we multiply them? We have to FOIL. So there's going to be a whole lot of reciprocals and FOILing going on. So if you're going to take 5 and divide it by some sort of complex number, the instructions say to simplify and then express your answer in a plus bi format, which is what the format of any complex number is. So 5 divided by this complex number, I don't know how to divide, but I do know how to multiply, so I'm going to change the thing that I don't know how to do into something that I do know how to do. 5, that would be 5 times the reciprocal. That would be 1 over 3 plus I. And so therefore, multiplying this is really just a 5 over 1. You multiply across, you get 5 plus 3i. This is technically like the finished version, but it's not in a plus bi format. So in order to get the I out of the denominator, that's really what it means by rationalizing the denominators, getting the I out so that you can express it in a more usable format. What we really have to do is we have to multiply it by a form of the number 1. Now, I'm not going to tell you how. I'm not going to tell you just yet exactly how I knew to multiply by 3 minus i. But let me just show you what happens when you do first. So if you multiply by this difficult thing right here, we got 3 minus I and 3 minus I, and so 5 times 3 minus I and 3 plus I times 3 minus I. Now, you can distribute the top, but you've got to FOIL the bottom. 3 times 3 is 9. Negative 3, the outside terms would be 3 times negative I, which is negative 3i. The inside terms is 3i. The last term is negative I squared, because minus I and positive I. But negative I squared turns into positive 1, because when you square it, this becomes negative of negative 1, which is positive 1. So, look at this. We've got 9 minus 3i plus 3i is plus 1. But wait a minute. The imaginary parts cancel. Minus 3i and positive 3i. Isn't that lucky? No, it's not luck. We arranged it. So you get 15. When you distribute, you get 15 minus 5i. And then 9 plus 1 is 10, and the imaginary parts cancel. So you can even split this up into a plus bi format. 15 over 10 is 15 over 10. Notice both of these have to be over 10. And then when you do that, you can simplify them and you get a plus bi. That's the format. That was a huge, long process. Let's do it a few more times just to get comfortable with the idea. And so we've got 5i, which is actually an imaginary number, divided by the complex number 3 plus 2i. I don't know how to divide, but I do know how to multiply. So I'm going to take the reciprocal, and I'm going to multiply now. 5i over 3 plus 2i, that's what it is. This is technically these two things multiplied by each other. This is, 5 divided by 3 plus 2i, that's 5i divided by 3 plus 2i. There it is. But we don't like i's in the denominator. It's not useful, it's not friendly, it's not helpful. You can't do a whole lot with it, and it's not an a plus bi format. So we've got to multiply by this strange thing over here, 3 minus 2i. And where did it come from? I'll tell you later. But check out what happens when I do. 5 times 3 minus 2i is what you get on the numerator, and then you'd have this thing you'd have to FOIL, because you're multiplying two different complex numbers, 3 plus 2i, 3 minus 2i. When you do that, the first term is 9, the outside term is negative 6, because 3 times negative 2i is negative 6i. The inside term is 2i times 3. The last term is negative 2i times 2i is negative 4i squared, which the negative here and the I squared cancel out. You just have 4, which is pretty awesome because the inside term and the outside term of the O and the I of FOIL are negatives of each other, and they cancel. And you're just left with 9 plus 4. In the numerator, you can distribute, and you get 15i minus 10i squared. So 9 plus 4 is 13. I squared is negative 1, and the minus and the negative cancel out. You just get plus 10. 10 plus 15i. If you're splitting it up into a plus bi format, you get 10 over 13 plus 15 over 13i. Whew. Wow, that's a long process. Let's do it one more time just to kind of solidify it. Okay, here we had division, and here we've got just a fraction bar. Remember, fractions and division are very related. This is not an a plus bi format, so then, and you might be like, Bergman, why do we got to have everything in a plus bi format? Why it's so important? Well, you'll see later why a plus bi format is so important, and it's just the way complex numbers are expressed. This is more complicated, and it's like not simplified. But if you can get it down to this, we'll say that this is a much more simplified version. Anyway, you can multiply. I'm not going to tell you where I got this 3 plus I and 3 plus I, but if you trust me on it, then we can move forward, and I'll tell you where I got it in just a moment. 18, let's see. Oh, we've got to FOIL twice. Once for the numerator, once for the denominator. Holy smokes, that's a lot of FOILing. 6 times 3 is 18. 6 times I is 6i. Negative 5i times 3 is negative 15i. Last is minus 5i times I is negative 5i squared, which is the same thing as 5, because I squared is equal to negative 1. It cancels. We got 3 minus I, and 3 plus I. Well, the first is 9, the outside is 3i, the inside is negative 3i, and the last is negative I squared. The I squared is equal to negative 1, so it's negative negative 1, which is just positive 1. I hope you're starting to see some patterns here, because it's the same basic process as you saw before. Now, the i's are not going to cancel in the numerator, because 18 plus 5 is 23, and 6 minus 15 is negative 9. So it's 23 minus 9i. But in the denominator, yes, 3i minus 3i cancel. We got 9 plus 1 is 10. And that's pretty awesome, because we have 23 over 10 minus 9 over 10i. A plus bi format. And how were we able to get it? Well, the key trick is to make sure you multiply it by just the right thing that's going to give you this cancellation, 3i minus 3i. I wonder how Bergman found this 3 plus I. All right, over here, 1 plus I over 2 minus 5i. You got 1 plus I over 2 minus 5i. The key here is to multiply it by just the right thing that's going to get rid of the imaginary numbers in the denominator. 2 plus 5i is what it is. And I'll tell you where I got it in just a second. First, we have to FOIL it twice. 1 times 2 is 2. Outside, 1 plus 5i is 5i. Inside, I times 2 is 2i. Last, I times 5i is 5i squared, which is the same thing as negative 5. Just make it negative, because I squared is equal to negative 1. First terms, 2 times 2 is 4. Outside term, 2 times 5i is 10i. Inside term, negative 5i times 2 is negative 10i. Last is negative 5i times 5i is negative 25i squared, which turns into positive 25. So if you write out all these terms, you get to here, and plenty of them are going to combine because they are like terms. 2 and negative 5, 5i and 2i combine, 4 and 25 combine, 10i minus 10i, they cancel, yeah, and you got nothing in the denominator except real numbers, which is awesome. It's definitely the goal. You can split up this fraction into negative 3 over 29 and plus 7 over 29i, a plus bi format. Golden. Big idea, you can divide complex numbers by multiplying by the reciprocal, which is great. Big idea number 2, you can rationalize the denominator a plus bi by multiplying it by a minus bi, which is a vocabulary word, which is its conjugate. A plus bi and a minus bi are called conjugates, and basically it's just if you saw a minus bi, you would say, oh, its conjugate is a plus bi, and that's the trick. At every moment, if I saw 3 plus I multiplied by 3 minus I over 3 minus I, and and that's really just it. That's how I got it. Thanks for playing along, y'all. Have a great night, and I'll see you in class tomorrow.